So I thought there's a lot going on here, so I decided I should record a video for this. So one question that was asked was, what's the difference between a removable discontinuity and a non-removable discontinuity? Well, back in pre-calc, algebra 2, certainly you should have seen it in pre-calc. We had things like you had to find x plus 2 times, you had these rational functions, let's just make this one up, over x plus 2. And they asked, okay, where's the vertical asymptotes? Are there any vertical asymptotes? Actually, let's add another thing in the denominator. How about x plus 1 or x minus 1? Okay. What you had to pay attention to was this factor here, the x plus 2 over the x plus 2. Well, those can cancel out, though we can't just forget about them. We can't pretend they're gone now. What that means is they'd be really what would be seen was just this rational function, x minus 5 over x minus 1. But what would happen with the x plus 2, or in other words, when x equals negative 2, it won't be a vertical asymptote, there'll be a hole in the graph. And that's when you get a removable discontinuity. This function is also discontinuous at x equals 1, but that's a vertical asymptote. And that's a non-removable discontinuity. There's nothing I can do to get rid of that vertical asymptote. Whereas the common factor, the x plus 2 over x plus 2, that tells me there's a hole. Just maybe I should finish this thought before I go on to the question here. So I'm seeing a rational expression, rational function. It's got a vertical asymptote of positive 1. I'm going to put a dotted line. It's got a 0 at x equals 5, right? Because that's if you set the top equal to 0, that's where you get the zeros for the function. And if you set the bottom denominator equals 0, that's where you get your vertical asymptotes. So I know this crosses the x-axis at, let's see, 1, 2, 3, 4, 5. So I know it crosses there. And then I see that this is the same power. Both of these functions have a degree of 1, so that's way out at infinity. So I'm trying to figure out if there's a horizontal asymptote. And you've done this this term. Well, if you're up to date, you've done this. And basically, when I'm finding the limit, to use some calculus terminology, the limit as x approaches positive infinity for this, or even negative infinity, the negative 5 and the negative 1 do not matter as much. That's basically, I'm going to have the same number over the same number, so that's 1. So that tells me there's a the limit is 1, and there's a horizontal asymptote at y equals 1. So, and I also got to think about, well, this is just the reciprocal function, and it's probably reflected. I know it's got to go through 0, 5, right? So I'm thinking this graph looks something like this, and it's going to have to come down like this. I could find the y-intercept. Let's see, the y-intercept is going to be when x equals 0, I get negative 5 over negative 1. So yeah, that's about right. Okay, so that's what that looks like. And what was I trying? Oh, but then I've got to think about at negative 2, I really should have this erased and have a hole here. Okay. And you can go check this out in desmos.com. It's probably a great way to check your graph. Graphing calculator also work. If you hit trace, if you're on your graphing calculator and you were to graph, well, just if you were to graph this whole original thing that I had up here, you would be able to trace it, hit trace, and then as soon as you hit negative 2, you'd see that you'd have an x value. X would say negative 2, and y would be blank. That means the function's not defined there. Okay, so a point removable discontinuity has a hole in the graph. The other thing you're going to see with a point removable discontinuity is sometimes they might have another point. So when x equals negative 2, they're saying the function's defined, and they're telling me some other value. This is also a point removable discontinuity. And here's the vertical the vertical asymptote, which is non-removable. There's no way I can get rid of that. There's some other kinds of non-removable discontinuities, which I hope you've seen already, this term. If you have a jump discontinuity, Actually, my on-the-ground our calculus class just talked about this last couple of days. So that's a jump discontinuity right here because it jumps from one side. The limit from the left is not the same as the limit from the right. That's a non-removable discontinuity. There's nothing I can do to make that continuous. See, the point removable discontinuity, I could fill that in. I could say, okay, well, when x equals -2 is not this number up here. It's going to be whatever. If I plug in -2, what is that? -7 over -3, so 7/3. Okay, so I hope that helps answer that question. Now let's see here. Let's see if I can't come back and you know what I'm going to probably try to do is erase this, and I'll paste in that question again. Oh, well, maybe I can't erase it. Oh, I know I can here. Let's see. We have the technology. I always erase something, right? Okay, so I don't know how well you can see that in this video. It's 5x cubed. Let's see. Let me write it larger. And I'm going to go to black ink. Sorry. Whoops, not red ink, black ink. Okay. Yep. There we go. Well, let's write with red ink, I guess. So I'm seeing 5x cubed minus 5x squared minus 10x. And I've got a 2x, it looks like cubed on the bottom, minus 2x. So they're asking us which of the following is false. So there's the x-axis asymptote. The x-axis is the asymptote of y equals f of x. Well, let's see. It is the equal power, right, of x to the third over x to the third. So that means I can ignore everything except the x to the third term. So 5x cubed over 2x cubed, because remember what I'm doing, I'm taking the limit as x approaches infinity. Okay, or negative infinity for that matter. And in that case, those cancel out. So, but I'm left with 5 over 2. So the x-axis, that would be y equals 0, is not a horizontal asymptote. Actually, the y equals 5/2 is. Okay, so there's that one's dead. Then they're telling me x equals 1 is an asymptote of it. Well, I don't know at this point. I'm going to have to do a little more work. It says the correct answer is the y-axis is an asymptote of. Okay, so let's check this out. So thinking back to what I just was rambling on about removable discontinuities. Ooh, okay. Boy, that paint program is messed up today. There we go. So what we got to do is factor everything. And I'm seeing the numerator. Well, actually, do I really need to factor everything? I do have to factor the denominator. I don't think I need to factor the, well, maybe I will. I'm gonna factor everything. So I'm gonna take a 5x out of the numerator. So as soon as I can get my pen back here. So I'm gonna factor out a 5x, and that leaves me x squared minus x minus 2. That's the numerator. And then I think x squared minus x minus 2 factors to x minus 2 times x plus 1. And then I've got a 5x on top. And the denominator can factor out a 2x. So I'm going to come over here and do that. So I'm going to factor out a 2x. So that leaves me x squared minus 1. And of course, x squared minus 1 is the difference of 2 squares. So 2x times x plus 1, x minus 1. So in this case, what's the common factor? I think there's a whole at x equals 0 because there's a common factor there. I'm also seeing a whole at x equals -1 because there's a common factor there. So that leaves, I'm going to have a vertical asymptote at x equals 1. I'm going to have a 0 at 2. So yeah, that's what I'm thinking. I'm thinking that there's a vertical asymptote of y equals 1. there's some couple of holes in our graph, and it has a horizontal asymptote of y equals 5/2. They're saying the y-axis is an asymptote of f of x. Oh, I don't know. I don't agree with that. I agree with this. I think that's the right answer. X equals 1 is an asymptote. Oh, this isn't the string. Now, it could be that this is a broken question. We might have to go take a look at it. See, I think that's the correct answer. Well, one thing we can do is we can certainly graph it. Let's see. Can I, let me try to go, let's see. I better write this down on paper because I'll never remember going to Desmos. Let's see, 5x to the third minus 5x squared minus 10x over 2x cubed minus 2x. Yeah, I think this is a broken question. Minus 3x. So what I'm going to do is I'm going to stop this share. And then I'm going to share, now let's go, what do I have for, here's a blank. I don't have anything confidential there on that screen. All right, so now I'm going to go out to desmos.com just because I got a screen share I can show you. I mean, I could do it with my grapher, but let's start graphing. So I'm seeing 5x raised to the third. I hope you know about desmos.com. It's a great website. It does calculus. Not quite where we're at yet, but okay, I think I've got that right. 5x cubed minus 5x squared minus 10x, and then divided by 2x raised to the third minus 2x. So let's see how I'm doing here. Let's go to projector mode so you can probably see it a little better. Now, I thought there was a hole at x equals 0, right? Let's see if I can get there. Oh, whoa, see that? Oh, my shaky hands. So there is a hole at x equals 0, so we're right there. There was also a hole at x equals +1. X equals -1. We thought there was a hole. Let's see if I can't find that. Yeah, see, there's the hole at -1. And then I thought there was a vertical asymptote at x equals 1, and I think that's, let's do x equals 1. Yeah, vertical asymptote at x equals 1. So I'm thinking that question's broken. The correct answer is actually C. Well, at least for this version of it, it had C. It's the vertical asymptote at x equals 1. So, I mean, scroll back through this video and see how I decided on that analytically without graphing. I mean, I guess, you know, will I know if we cheat? No, but the AP readers will next summer, right? So that's what I'm thinking about that question. So we went over point removal discontinuities, non-removable discontinuities, and then how do you deal with vertical asymptotes? How do you factor those terms and everything? So I hope this helps you move on, and if you need some live help, don't hesitate to grab an appointment. And I use this Zoom software that I'm recording on this, and it works really well, especially if you get a mic and you're not too embarrassed to talk to me. We'll probably never meet, guys, so I mean, it's certainly all right to do this. Okay, so I'm going to stop recording and talk to you later.